Hello everybody. We will be talking about equipotential surfaces and their relation to the electric field. So what is an equipotential surface? From its name, an equipotential surface is the surface that exists within the vicinity of an electric field but has the same potential on it. So the potential difference on that surface is zero. Okay, let's actually try to understand that better. Let's say we have a charge here, all right, and this charge has it's a positive charge and has all its electric field lines going radially outward like that. Okay, if you actually have a point now here that exists around this positive charge, let's say this is a positive test charge, and now we want to find the potential at this point due to this charge. We can find it this way. V is equal to KQ over R. Okay? KQ over R. Q is this red test charge and R is this distance. Okay? And K is a constant 9 times 10 to the power 9. Alright? Now, any place around the charge that forms a complete circle, okay, and has the same distance r, will have the same potential, okay, and the name comes equipotential surface. Now notice these equipotential surfaces are always going to be perpendicular to the electric field lines. So these equipotential surfaces are perpendicular to the electric field line, and the same here. The same here. They're always what? Perpendicular. And they form a surface where the potential difference on that surface is equal to zero. Because if you calculate V here and V here, and if you calculate, let's call this one V1 and call this one V2, so delta V will be equal to zero. That's what I mean, the potential difference on the equipotential surface is equal to zero. Also, the thing about these equipotential surfaces is that if you have a charge, another charge here, let's call this Q1, and you want to move this charge this way or this way on the equipotential surface, you can move this charge without consuming energy. You don't have to spend energy to move this charge. What you basically do, if you want to, figuratively speaking, if you just touch this charge on the equipotential surface with your finger and you were able to move it on this equipotential surface, it will go around and around and around without basically stopping. That's usually not the situation, not like does not happen really, but this is what it is. Okay? If you're actually not sure about the equipotential surface, let's actually look at the gravity, okay? So this is Earth, like you have here. And these are nice little, let's say, roses. And you have a ball here. If you move the ball this way or this way, you are actually not required, you don't have to spend work. We know work is equal to what? FD cosine theta. Okay? If you are carrying a ball like this here, you are probably carrying it with applying a force this way, but you're moving the ball this way, so that's D. The angle, as you can see, is 90 degrees. Cosine 90 is 0, so the work is 0, so you don't need to spend energy to move the ball this way or this way, okay? We know if the ball is released, it's going to go down. That's because of gravity, and that's true, the same thing for the charge. If this charge is released, it's going to go either get repelled or get attracted to this test charge, depending on the type of this charge. So this is just to get you a better idea about the equipotential surface. So this here is called equipotential surface for gravity. This here is equipotential surface for gravity. This one here is the same. Now, if we want to identify more or talk more about equipotential surfaces, let's look at this parallel plate capacitor. Let's say this parallel plate capacitor here is positive and now this one here part is negative, we know that the electric field lines go from the positive of higher potential to the negative or lower potential. So there we have electric field lines that are going this way. Okay, if you put a charge on an equipotential surface, let's assume this is an equipotential surface. Let's assume this is an equipotential surface here. And you put a charge here. This charge can be moved on this equipotential surface anywhere without actually spending any work, because the potential on this surface here is always equal. It's the same. So delta V on this surface is equal to 0. But there is a potential difference between this guy and this guy. And there's a potential difference between this equipotential surface and another equipotential surface here. Okay? There is millions and millions, infinite number of equipotential surfaces, but these are imaginary ones, of course. So basically, and always, look, the equipotential surfaces, they do not intersect. They're always perpendicular to the electric field lines, so they follow all the same rules. And as you can see, I drew these equipotential surfaces a little bit smaller than the parallel plate capacitor plates, and the reason is because there is an edge effect here at the edge of the electric plates. All right, so that may actually skew the potential equipotential surfaces here around the edges. Okay, so let's actually study this more too. So let's say we have an electrode here. An electrode is just like a metal that has been charged. So this electrode, a piece of metal that has been charged, that looks like what? A circle. And here it looks like a circle too. One of them is positive, one of them is negative. We know the electric field lines go from here to here. Okay. And remember, the electric field lines always perpendicular to the surface. Okay. Now, if you want to draw the equipotential surfaces, so the equipotential surfaces kind of like around. Okay, and they form what? Make sure they form always a 90 degrees angle with the electric field lines. All right, so they go around like this. Right, now maybe these ones here look like that. So they don't usually have to look like circular or perfect plates or whatever. They could be, you know, they're subject to many forces, but mostly the electric field lines. So you want to make sure that they are always perpendicular to the electric field line. They do not cross or whatever. So these are all called equipotential surfaces. Okay. Now there is, you know, an experiment you can do how to find the equipotential surfaces, and you can actually bring, for example, a voltmeter. So a voltmeter. So it's an electric device that measures the electric potential difference. And once you measure the electric potential difference between these two plates, you will find that the electric potential difference V is max. Okay, whatever that is, maybe 9 volts, 200 volts, doesn't matter. Now, if you move this to a closer point, so if you delete this one out and you move it to a closer point to this plate, you will measure a potential difference that is less than this point, so less than max. Okay, and if you keep taking this so that you can measure the potential difference, so let's use another voltmeter here, and you put one part of the voltmeter here and the other part of the voltmeter here, so you're measuring the voltage difference on the same plate, then you will measure the potential difference to be equal to 0. That's an experiment that you can do in the lab if you want to. But this is all about qualitative analysis of what equipotential surfaces are. I hope this helped a little bit. Okay, so let's look more now into parallel plate capacitor. So if there is an electric field, as you can see, electric field goes from here to here, so that's the electric field. And the distance between the two parallel plate capacitors is known as the distance D. Now we know that we have a potential difference between this plate and this plate. Okay, now this potential difference, let's call it just what? V, okay, for now. Now, what is the relationship between V, E, and D? Or what is the relationship between the potential difference, the electric field, and the distance between the plates? Okay, there's a way to do that, but let's look at a point charge. So if we have a point charge here, okay, and this point charge radiating, as you know, electric field lines all over the place, okay, and we want to find out here, just like we did up a little bit here, okay, we want to find out the potential here. So the potential V here is equal to, as we know, KQ over R. But if we want to find what the electric field at this point, so this is a point, we want to find out what the electric field at this point, the electric field is basically equal to KQ over R squared. Okay, now look at this equation very carefully. This equation, the voltage, okay, and this one is K, there is K here, there is Q, there is Q, there is R, but there is here R squared. So if you want to kind of like by hand waving, this is not like exactly like a good derivation, but it's a working derivation. It works. If you want to look at what the relationship between V, E, and the only thing that is different, there's Q, 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 K, K and Q goes away. Okay, so let's divide all of this together. So I'm going to say V over E. So I'm dividing this equation by this one. V over E is equal to K and Q cancel with each other. What you have left is what? 1 over R divided by 1 over R squared. Okay? Now with some quick, so this is equal to 1 over R times basically R squared over 1 if I want to. So R squared with R goes away. So V over E is equal to R. Okay? Or you can say simply that the voltage is equal to E times R. So if we take this to the parallel plate capacitor, and that's a good relationship actually. There's a lot of things we had to do. Of course, for example, E is a vector quantity. The potential is not. So there, the good way to derive this equation is using calculus. But this is beyond the scope of this class. All right. So now we have, if we look at this equation and compare it here, then you can say that the voltage difference across a parallel plate capacitor is basically equals E times D. And that's a good equation to know. That's a very good equation to know. All right? So you can find the potential once you know the electric field and the distance between the two parallel plate capacitors, between the two parallel plates in the parallel plate capacitor. Okay? And that's it for equipotential surfaces. Thank you very much. Bye-bye.